In November 1944, a P-51D Mustang made an emergency landing in Japanese-controlled Manchuria, its engine damaged by ground fire during a reconnaissance mission over northern China. The American pilot was captured, but his aircraft, the most advanced fighter the Allies had deployed to the Pacific, theater fell into Japanese hands nearly intact. Within 2 weeks, the Silver Fighter with its distinctive laminar flow wings was sitting on a test ramp at Fusa Airfield, 40 kilometers west of Tokyo, surrounded by engineers and pilots who had been ordered to discover why American fighters were sweeping Japanese aircraft from the skies with devastating efficiency. What they found would trigger classified reports that traveled all the way to the Emperor's advisors, emergency meetings at the Navy Ministry, and a final, desperate realization that Japan was fighting an enemy whose industrial and engineering capabilities had surpassed their own by a margin so wide that no amount of spirit, sacrifice, or tactical brilliance could close it. This is the story of truth confronting mythology, of data contradicting doctrine, and of the men who had to write the reports that confirmed Japan's defeat in the air war. If you're looking for the real stories behind World War II's air war, the engineering intelligence that shaped outcomes, and the human cost of technological gaps, subscribe right now. We're bringing you primary source history from archives most people never access. Let's begin. November 18, 1944. A Fusa Airfield, Fusamachi, Tokyo Prefecture, Japan. The morning's cold, winter settling over the Kanto plain with gray skies and wind that carries the smell of agricultural fires and distant factories. Commander Minoru Genda stands on the concrete apron, arms folded across his chest, studying the aircraft that sits before him like a challenge, like an accusation, like proof of everything he has feared for the past year. The North American P-51D Mustang, serial number 4414888, tail number B7L, belongs to the 23rd Fighter Group 76 Fighter Squadron based at Luliang Airfield in China. The aircraft crash-landed on November 3rd near Changchun, Manchuria, during a long-range reconnaissance mission. The pilot, Captain James Mitchell, 26 years old, from Oregon, survived the landing but was captured by Kwantung Army troops, interrogated for 3 days, then transferred to a POW facility outside Mukden. His aircraft was more fortunate or less fortunate depending on perspective. It was transported by rail to Korea, then by ferry to Shimonoseki, then by rail again to Fusa, arriving 5 days ago. Now sitting on Japanese soil waiting to reveal its secrets. Genda is 40 years old, the same age he was when he planned the Pearl Harbor attack 3 years ago. He has aged a decade in those 3 years. The early victories, the string of conquests across the Pacific, the sense of invincibility, all of it has dissolved into a war of attrition that Japan is losing. He has seen the intelligence reports, the reconnaissance photographs, the after-action analyses. American aircraft production exceeds Japanese production by ratios that seem impossible. American pilot training produces thousands of competent aviators, while Japanese training schools struggle to graduate hundreds. American technology, dismissed as crude and uninspired in 1941, has surpassed Japanese technology across nearly every domain. And now, sitting before him, is the physical embodiment of that superiority. A fighter aircraft so advanced, so capable, so thoroughly dominant that Japanese pilots encountering it in combat rarely survive to file reports. Genda is here to fly it, to measure its capabilities, to document the truth. He is not looking forward to what he will discover. Behind Genda, 3 other pilots wait in the cold morning air. Commander Saburo Sakai, 28 years old, one of Japan's highest-scoring aces with 64 confirmed victories. Partially blinded in one eye from a combat wound, but still flying, still fighting, still refusing to accept that the war is lost. Lieutenant Commander Hiroyoshi Nishizawa, 24 years old, with 87 confirmed kills. The most lethal pilot in the Imperial Japanese Navy. A man whose skill is legendary, whose personal demons are equally legendary, who flies because combat is the only place he feels alive. And Captain Yasuhiko Kuro, 23 years old, a test pilot from the Naval Air Technical Arsenal at Yokosuka, an engineer by training, a pilot by aptitude, brought to Fusa specifically to conduct technical evaluation of captured enemy aircraft. Each man has his assignment. Genda will conduct initial flight evaluation, assessing handling qualities and general performance. Sakai will conduct tactical evaluation, simulating combat scenarios and determining tactical advantages or disadvantages. Nishizawa will conduct high-speed and high-altitude testing, pushing the aircraft to its limits. Kuro will conduct instrumented testing, recording precise performance data for engineering analysis. Together, they will determine whether the P-51D Mustang is as dangerous as combat reports suggest. Genda suspects they will confirm that it is worse. The Mustang has been made airworthy by a team of Japanese technicians over 5 days of intensive work. The Packard V16507 engine, a license-built version of the British Rolls-Royce Merlin, had sustained minor damage from the ground fire that forced the landing. Two-cylinder heads were cracked, oil lines were severed, the coolant system was compromised. Japanese engineers, working with limited spare parts and no maintenance manuals, repaired what they could and fabricated what they could not repair. The cylinder heads were replaced with units machined at Nakajima Aircraft, copied from measurements of the damaged originals. The oil lines were fabricated from available tubing. The coolant system was flushed and filled with a mixture that approximated the American glycol water solution. The result is functional but precarious. The engine will run, will produce power, but whether it will survive extended operation is unknown. The hydraulic system was simpler to repair, requiring only new seals and fluid. The electrical system required more extensive work. With Japanese technicians tracing wiring diagrams they recreated by reverse engineering the aircraft systems. The armament, 6.50 caliber Browning M2 machine guns, 3 in each wing, was test-fired yesterday. All 6 weapons functioning perfectly. The firepower is formidable, heavier than any Japanese fighter, equivalent to a bomber's defensive armament. Genda walks slowly around the Mustang, examining every detail with the eye of an engineer and the instinct of a combat pilot. The aircraft is larger than he expected, longer and heavier than intelligence estimates suggested. The all-metal construction is immediately apparent, with flush-riveted aluminum skin that is smoother than any Japanese aircraft. The wings are thin, with a distinctive laminar flow airfoil that looks almost knife-like in profile. The canopy is a bubble, a single-piece plexiglass dome that provides 360-degree visibility, far superior to the framed canopies on Japanese fighters. The landing gear is robust, the tires are large, the braking system appears sophisticated. Everything about the aircraft suggests strength, durability, industrial sophistication. The Zero, by comparison, is delicate, lightweight, optimized for performance through minimal structure. The Mustang is optimized for survivability through strength. 2 philosophies, 2 approaches. Genda knows which approach is winning the war. A Japanese mechanic, Petty Officer First Class Takeshi Yamada, approaches to provide the cockpit briefing. Yamada was a civilian aircraft mechanic before conscription, trained at Mitsubishi Heavy Industries. Assigned to technical intelligence work because of his mechanical aptitude and his ability to read basic English. He has studied the Mustang for 5 days, experimenting with controls, consulting captured American technical manuals, interviewing the American pilot before he was transferred to the POW camp. Yamada explains the startup procedure: battery on, boost pumps on, throttle cracked open 1 inch. Mixture full rich, propeller full forward, magnetos to both, press starter button. The procedure is similar to Japanese aircraft but with more electrical complexity. He warns that the Merlin engine is sensitive to coolant temperature, that overheating will cause catastrophic failure within minutes, that the coolant temperature gauge must be monitored constantly. He also warns about the tremendous power the engine produces. 1,695 horsepower at war emergency power, nearly double the power of the Zero Sakai engine. This power requires respect, requires careful handling, requires understanding that the aircraft will behave differently than anything Genda has flown before. Genda nods, absorbs the information, climbs the wing route to the cockpit. The cockpit is spacious, far larger than a Zero's cramped interior. The seat is adjustable, comfortable, with thick cushioning and excellent lumbar support. American pilots, Genda thinks, are comfortable. Japanese pilots are Spartans. The instrument panel is logically arranged with large, easily readable gauges. Airspeed indicator, altimeter, vertical speed indicator, turn and bank indicator, artificial horizon. Directional gyral, standard instruments, but higher quality than Japanese equivalents, with clearer markings and smoother movements. The engine instruments are comprehensive: manifold pressure, RPM, fuel pressure, oil temperature, coolant temperature, cylinder head temperature. The Zero has fewer instruments, relying on pilot judgment for many parameters that the Americans measure precisely. The throttle quadrant on the left side features 4 controls: throttle, propeller pitch, mixture, and a small lever marked cooler. Yamada explained that this controls the radiator flap, though normally it operates automatically. The electrical panel features more switches than Genda has ever seen in a fighter aircraft. Navigation lights, landing lights, recognition lights, gun heater, pitot heat, radio instruments. The complexity is impressive and slightly intimidating. Japanese fighters are simple. This aircraft is sophisticated. Genda settles into the seat, adjusts the rudder pedals, tests the control stick. The stick is centrally mounted, smooth and positive in movement. The control forces feel heavier than a Zero, requiring more effort to move, but the responses are predictable and linear. He locates the gun sight, a K-14 gyroscopic computing sight, far more advanced than the simple ring and bead sights on Japanese fighters. The sight can calculate lead automatically, adjusting for target range, speed, and angle off. American pilots have computers helping them shoot. Japanese pilots have skill and practice, technology versus training. Genda knows which one wins when pilots are evenly matched. He runs through the startup checklist, committing each step to memory, then signals Yamada that he is ready. Yamada climbs down and Genda is alone with the enemy machine. Batteries switch on. The instrument panel illuminates, gauges coming to life. Fuel boost pumps on, 2 electric pumps humming, pressurizing the fuel system. Throttle open 1 inch. Mixture control full rich, propeller control full forward. Magneto switches to both. He presses the starter button. The engine cranks slowly, the massive 4-bladed Hamilton standard propeller rotating through compression strokes. Once, twice, 3 times. Then the engine catches with a deep, smooth roar that is nothing like a Japanese engine. The Sake engine in a Zero rattles and barks, mechanical and harsh. The Merlin purrs smooth and powerful, a sound that communicates confidence and strength. 12 cylinders firing in perfect sequence, each exhaust stack ejecting flame and noise, the whole engine vibrating with contained power. The propeller spins up, the cockpit fills with the smell of exhaust and oil, and Genda feels the aircraft come alive beneath him. This is an enemy machine, he reminds himself. This is the weapon that is killing his comrades, destroying his nation's air force, sweeping Japanese aircraft from the skies. He needs to understand it. He needs to measure it. He needs to know exactly how badly Japan is losing this fight. He checks the engine instruments as the Merlin warms. Oil pressure climbs to 90 psi, normal. Coolant temperature rises slowly toward operating range. Cylinder head temperatures stabilize around 120 degrees Celsius. Fuel pressure shows 15 psi from the boost pumps. Everything is functioning normally. He tests the magnetos, switching from both to left, checking for RPM drop. Minimal drop, 25 RPM, indicating healthy ignition. Switch to right magneto, same result, switch back to both. He cycles the propeller pitch control, watching the RPM change as the blade angle adjusts. The constant speed propeller system works smoothly, maintaining RPM automatically as power changes. Japanese constant speed systems are less sophisticated, requiring more pilot management. He tests the flight controls, moving the stick and rudder through full travel, watching the external surfaces move. Ailerons, elevator, rudder, all responding correctly. He is ready to taxi. He releases the toe brakes and advances the throttle slightly. The Mustang rolls forward, heavy but responsive. The brakes are hydraulic, powerful, giving precise control. He has sterns toward the taxiway, looking around the long nose, the forward visibility on the ground poor but manageable. The nose is longer than a Zero's, the view more obstructed. But the bubble canopy allows him to see to the sides and rear better than any Japanese fighter. Trade-offs. Everything is trade-offs. He reaches the runway threshold, turns into the wind, runs through his pre-takeoff checks. Mixture rich, propeller full forward, maximum RPM, radiator flap automatic, elevator trim set slightly nose up for takeoff. Fuel selector on main tank, magnetos both. Coolant temperature 105 degrees Celsius within range for takeoff. He glances down the runway, 1,200 meters of concrete stretching ahead. More than enough. He advances the throttle to full power. The acceleration is violent, instantaneous, shocking. The Merlin howls, the propeller claws the air, and the Mustang rockets down the runway like it has been launched. Genda's head snaps back against the headrest, the acceleration crushing him into the seat. He has never experienced anything like this in a fighter. The Zero accelerates gently, gracefully, building speed gradually. The Mustang accelerates like a race car, like a rocket, like something that was designed for pure speed. He fights the torque, feeding in right rudder, heavy right rudder, the aircraft wanting to swing left despite his inputs. At 65 miles per hour, the tail lifts. At 95 miles per hour, he eases back on the stick, and the Mustang leaps into the air, climbing away from the runway with breathtaking authority. He retracts the landing gear, watching the wheels fold up into the wings with smooth hydraulic precision. He retracts the flaps. The Mustang accelerates even faster, the airspeed indicator unwinding rapidly. He reduces power to climb setting, 46 inches of manifold pressure, and 2,700 RPM, and the Mustang climbs at 3,800 feet per minute. The Zero climbs at 22,600 feet per minute. The Mustang is climbing 45% faster. Genda is 3 minutes into the flight, and already the data is devastating. He levels at 10,000 feet, the climb taking less than 3 minutes, and begins basic handling tests. Turns to the left, turns to the right, steep banks at 45 degrees, then 60 degrees. The Mustang responds smoothly, predictably, with control forces that are higher than a Zero, but not excessive. The roll rate is good, approximately 90 degrees per second at 300 miles per hour, comparable to a Zero. The turn rate is adequate, not exceptional, the aircraft's heavier weight limiting its ability to sustain high G turns. In a pure turning fight, the Zero would have an advantage. Agenda realizes immediately that American pilots would never fight that way. Why would they turn when they can run? He tries a loop. The Mustang loops easily, maintaining energy throughout, requiring minimal altitude loss. The Zero loops more tightly but loses more energy. He tries a barrel roll. The Mustang rolls smoothly, taking about 3 seconds for 360 degrees. The Zero rolls slightly faster. But these maneuvers, these traditional dogfighting tactics, are irrelevant against an aircraft that can simply refuse to dogfight. Jenda levels at 15,000 feet and begins speed testing. He advances the throttle to military power. 61 inches of manifold pressure and 3,000 RPM. The Mustang accelerates rapidly, the airspeed building with shocking speed, 300 miles per hour, 350 miles per hour, 380 miles per hour. Still accelerating. The aircraft is rock solid, no vibration, no buffeting, the controls remaining light and responsive, 400 miles per hour. The Zero's maximum speed at this altitude is 332 miles per hour. The Mustang is flying 103 miles per hour faster, over 30% faster. Jenda maintains this speed for 5 minutes, monitoring the engine instruments obsessively. Coolant temperature is 115 degrees Celsius, approaching the upper limit but stable. Oil temperature is normal. The engine is producing full power without complaint. This is not maximum performance. This is military power, sustainable indefinitely. The Mustang can cruise at speeds the Zero cannot achieve even in a dive. He climbs to 20,000 feet and repeats the speed test. The results are equally disturbing. The Mustang reaches 440 miles per hour at military power. The Zero's maximum speed at 20,000 feet is 336 miles per hour. The performance gap is widening with altitude. He climbs to 25,000 feet, the altitude specified in his test protocol. The altitude where the Japanese Army Air Force claims the Nakajima Ki-84 Hyatt can compete with American fighters. He levels off, allows the airspeed to stabilize, then advances the throttle to war emergency power. 67 inches of manifold pressure and 3,000 RPM. The Merlin responds instantly, the manifold pressure gauge climbing as the supercharger boosts, the engine howling with unrestricted power. The Mustang accelerates. 380 miles per hour, 400 miles per hour, 420 miles per hour, 435 miles per hour, 440 miles per hour. The airspeed stabilizes at 440 miles per hour at 25,000 feet. Jenda maintains this speed for 10 minutes, watching the coolant temperature climb slowly. It peaks at 121 degrees Celsius, just below the red line, then stabilizes as the automatic radiator flap adjusts to increase cooling. The engine is operating at maximum power, at high altitude, in stable condition. No Japanese fighter can match this. Not the Zero, not the Shidan, not the Hyatt, not anything Japan has in production or development. Jenda tries to process the tactical implications. If American fighters can fly at 440 miles per hour at 25,000 feet, they control every aspect of air combat. They can engage when they choose. They can disengage when they choose. They can attack from any angle. They can escape from any pursuit. Japanese fighters are simply too slow to force combat on unwilling American pilots. The only advantage Japanese pilots retain is maneuverability at low speeds, which is useless if the engagement never reaches low speeds. Speed is life, the Americans say. Jenda understands now what that means. Speed is choice. Speed is control. Speed is invincibility. Japan has no answer to this speed. He conducts climb tests, timing the ascent from sea level to various altitudes. The data is recorded by Kuro, who is watching from the ground with binoculars and a stopwatch, timing the climb against altitude markers. Sea level to 10,000 feet, 2 minutes 40 seconds. 10,000 to 20,000 feet, 4 minutes 15 seconds. 20,000 to 25,000 feet, 3 minutes 30 seconds. The Mustang's climb rate remains excellent throughout, barely degrading until above 28,000 feet, where the supercharger's effectiveness begins to diminish. The Zero takes 7 minutes 30 seconds to reach 20,000 feet. The Mustang reaches the same altitude in under 7 minutes. In a scramble situation, the Mustang would be at interception altitude while Japanese fighters were still climbing. The Americans can position themselves advantageously before Japanese fighters even arrive at combat altitude. This is not a fair fight. This is a massacre. He tests high-altitude performance climbing to 30,000 feet. The Mustang's performance remains strong, the Merlin's two-stage supercharger continuing to provide excellent power. Maximum speed at 30,000 feet is 425 miles per hour. The Zero at 30,000 feet is barely flyable, the engine struggling, the controls mushy, the maximum speed perhaps 290 miles per hour. The Mustang owns the high-altitude fight completely. He climbs to 35,000 feet, near the aircraft's service ceiling. The performance is degraded but still adequate. Speed at this altitude is approximately 380 miles per hour, and the aircraft remains controllable, responsive. No Japanese fighter can operate effectively at 35,000 feet. The Americans can fly above Japanese fighters, dive on them at will, attack without fear of counterattack. The altitude advantage alone is decisive. He tests dive performance, rolling inverted and pulling through into a vertical dive from 30,000 feet. The Mustang accelerates rapidly, the airspeed building with frightening speed. 400 miles per hour, 450 miles per hour, 500 miles per hour. The control forces increase dramatically, but the aircraft remains stable. No flutter, no buffeting, no indication of structural distress. At 550 miles per hour, indicated airspeed, Jenda begins the recovery. He pulls back on the stick with both hands. The force is tremendous. His vision tunneling as G-forces exceed 6, but the Mustang pulls out smoothly. The structure solid, the wings undeformed. He levels at 15,000 feet, having lost 15,000 feet in the dive. The Zero cannot dive safely beyond 410 miles per hour without risk of structural failure or control surface flutter. The Mustang can dive at 550 miles per hour without strain. American pilots can dive to escape or dive to attack, building speed that Japanese pilots cannot match, pulling out at altitudes where Japanese aircraft would disintegrate. The dive advantage compounds the speed advantage, making the Mustang untouchable. After 2 hours of flight, Jenda returns to Fusa. The landing is straightforward. The Mustang touching down at 95 miles per hour, the landing gear absorbing the impact smoothly, the brakes bringing the aircraft to a quick stop. He taxis back to the apron, shuts down the engine, sits in the cockpit for 2 full minutes without moving. He's trying to understand what he has just experienced. He has flown the best fighter aircraft in the world. It is not a Japanese aircraft. It is an American aircraft. The performance gap is not marginal. It is categorical. At every altitude above 15,000 feet, the Mustang is simply faster. At every combat parameter that matters, speed, climb, dive, altitude performance, energy retention, the Mustang is superior. The Zero retains advantages in low-speed maneuverability and perhaps in very low-altitude performance. But these advantages are tactical dead-ends. American pilots will not fight where Japanese fighters have advantages. They will fight where they have advantages. And they have advantages everywhere. Sakai is waiting as Jenda climbs down from the cockpit. Sakai, with his 64 victories, his damaged eye, his reputation as one of Japan's most skilled pilots, asks what Jenda found. Jenda looks at him and says, "Everything we feared is true. This aircraft is better than the Zero in every way that matters in modern air combat. We cannot compete with this. We cannot force these aircraft to fight on our terms. American pilots flying Mustangs can kill us whenever they choose, and we cannot stop them." Sakai's face remains expressionless, but something flickers in his one good eye. Not surprise, confirmation. He has fought against Mustangs over the Philippines. He knows what they can do. He just needed someone to quantify it, to measure it, to confirm that the problem is not poor Japanese tactics or insufficient training. The problem is the aircraft, the hardware, the engineering. Sakai flies next. Sakai's flight profile is tactical, testing the Mustang in scenarios that simulate combat. He performs mock interceptions, accelerating from cruise speed to combat speed, measuring how quickly the Mustang can respond to threats. He discovers that the Mustang can accelerate from 300 miles per hour to 400 miles per hour in 35 seconds at 20,000 feet. The Zero requires over a minute to accelerate through the same speed range and cannot even reach 400 miles per hour at that altitude. Response time is critical in combat. The Mustang responds twice as fast as the Zero. He performs mock pursuit curves, attempting to follow an imaginary enemy through turning maneuvers. He discovers that the Mustang's high-speed handling is excellent, maintaining control effectiveness at speeds where the Zero's controls become heavy and unresponsive. Above 350 miles per hour, the Mustang can turn tighter than the Zero because the Zero's controls stiffen while the Mustangs remain responsive. The Americans have engineered away the control problems that plague high-speed maneuvering in Japanese fighters. He performs mock defensive maneuvers, simulating what a Mustang pilot would do if attacked by Japanese fighters. He discovers that the Mustang can simply accelerate away, building speed that no Japanese fighter can match, opening the range, escaping the threat. If the American pilot maintains discipline, refuses to turn, just pushes the throttle forward and runs, the Japanese fighter cannot catch him, cannot force combat, cannot achieve a firing solution. The Japanese pilot can only watch as the Mustang pulls away, out of range, out of reach, untouchable. Sakai, executing these maneuvers, realizes that every tactical principle he has learned in 4 years of combat is obsolete. Cutting the corner, using vertical maneuvers, energy management. All of these tactics assume comparable performance between opponents. When one opponent is 100 miles per hour faster, these tactics fail. The slower aircraft cannot cut corners fast enough, cannot regain altitude fast enough, cannot force the faster aircraft to make mistakes. The Mustang pilot only has to fly straight and fast. That is enough. He tests the Mustang's firepower by making simulated gun passes against ground targets, using the K-14 gun sight to aim. He discovers that the sight is remarkably accurate, automatically computing LED, adjusting for range and deflection. Japanese pilots use iron sights, estimating LED through experience and intuition. American pilots have computers calculating for them. The technology removes uncertainty, makes mediocre marksmen into effective shooters. He estimates that an average American pilot with the K-14 sight would achieve hit probabilities comparable to an experienced Japanese pilot with iron sights. But the average American pilot is also flying an aircraft that is 100 miles per hour faster, which means he gets more shooting opportunities, easier approach angles, less time exposed to return fire. Technology multiplying tactics multiplying performance equals dominance. Sakai lands after 90 minutes, climbs down, says nothing to anyone. He walks away from the aircraft, lights a cigarette, stands alone smoking for 10 minutes. When Kuro approaches to ask what he found, Sakai looks at him and says, I understand now why we're losing. Nishizawa flies third, pushing the Mustang to its absolute limits in ways that Genda and Sakai, cautious and methodical, did not. He performs violent snap rolls at maximum speed, discovering that the Mustang's roll rate peaks at 110 degrees per second at 400 miles per hour, faster than any Japanese fighter. He performs sustained 6G turns at high speed, discovering that the Mustang can sustain these turns without stalling or losing control. Its high wing loading and powerful engine providing excellent high-speed turn performance. He performs zoom climbs from low altitude, diving to build speed, then pulling vertical, discovering that the Mustang can trade speed for altitude with extraordinary efficiency, climbing 8,000 feet from a 5,000-foot altitude base after a 450 mile per hour dive. Energy fighting. Boom and zoom. These are the tactics the Mustang enables. The tactics that negate Japanese maneuverability advantages. The tactics that are killing Japanese pilots daily over China and the Pacific. Nishizawa performs high-speed passes, accelerating to maximum speed at various altitudes, confirming Genda's findings. At 20,000 feet, 440 miles per hour. At 25,000 feet, 440 miles per hour. At 30,000 feet, 425 miles per hour. The Mustang's speed is consistent across a wide altitude band. The Merlin engine's two-stage supercharger maintaining power where Japanese single-stage superchargers lose effectiveness. He tests the Mustang's spin characteristics by deliberately stalling the aircraft at 10,000 feet and allowing it to enter a spin. The Mustang stalls cleanly with clear warning buffet, drops a wing gently and enters a stable spin. Recovery is standard, opposite rudder, stick forward, wait for rotation to stop, recover from the dive. The Zero's spin characteristics are less forgiving, often entering flat spins that are difficult or impossible to recover. American pilots can make mistakes and survive. Japanese pilots cannot afford mistakes. He tests the Mustang's maximum dive speed by rolling inverted at 35,000 feet and pulling through into a vertical dive. The airspeed builds rapidly, passing through 500 miles per hour, 550, 600. At 610 miles per hour indicated airspeed, Nishizawa begins the recovery. The stick forces are tremendous, requiring both hands and significant strength, but the aircraft pulls out, the structure holding, no flutter, no failures. He levels at 10,000 feet, his vision having grayed completely during the pullout, his hands shaking from the physical effort. 610 miles per hour. The Zero would have disintegrated. The Mustang survived. Structural strength. Over-engineering. American design philosophy values survival over elegance. Nishizawa lands after 2 hours, climbs down, looks at the Mustang with something close to hatred, and walks away without speaking. Kuro flies last, conducting instrumented tests with recording equipment he has installed in the fuselage section behind the cockpit. The equipment includes accelerometers, pressure sensors, temperature probes, and a movie camera pointed at the instrument panel, recording all gauge readings throughout the flight. Kuro's flight lasts 3 hours, systematically testing every performance parameter. He maps the power curve, documenting horsepower output at various altitudes and power settings. He maps the drag curve, measuring deceleration rates at various speeds. He maps the fuel consumption curve, documenting fuel flow at various power settings. He documents control forces, measuring stick and rudder loads at various speeds and configurations. Every test produces data that will be compiled into performance charts, engineering analyses, technical reports. Objective truth. Numbers that cannot be disputed. Kuro is an engineer. Engineers do not argue with data. The data says the P-51D Mustang is superior to every Japanese fighter in every performance category that matters above 15,000 feet. The data says Japan is losing the air war because Japanese aircraft are inferior. The data says this will not change because Japan lacks the industrial capacity and technological sophistication to build aircraft like the Mustang. Kuro lands, downloads his recording equipment, begins processing the data. He does not need to complete the analysis to know what the conclusions will be. November 20th, 1944. The 4 pilots gather in a commandeered house 3 kilometers from Fusa Airfield, now serving as their temporary headquarters and documentation center. The house is traditional Japanese construction, wood and paper, heated by charcoal braziers that provide inadequate warmth against the November cold. Tatami mats cover the floors. A low table dominates the center room, covered with charts, graphs, performance data sheets, photographs of the Mustang. Genda has been writing the report for 2 days, working with Kuro's data, organizing observations, formulating conclusions. The report is 63 pages, handwritten in careful characters on military forms. The opening section provides background: the Mustang's capture, its transport to Japan, its repair and preparation for flight testing. The second section documents the test protocols: who flew, when, what tests were conducted, what data was collected. The third section presents the performance data: speeds at various altitudes, climb rates, dive performance, turning performance, all compared against the A6M0 and the Ki-84 Hyatt. The comparisons are devastating. The Mustang is faster at every altitude above 5,000 feet. The Mustang climbs faster. The Mustang dives faster and more safely. The Mustang has longer range, better armament, superior visibility, stronger structure, more reliable engine, more sophisticated systems. The Zero retains advantages only in low-speed maneuverability and possibly in very low-altitude performance below 5,000 feet. These advantages are tactically irrelevant because American pilots will not fight where these advantages matter. The fourth section, the conclusions, is the most important and the most dangerous. Genda writes carefully, choosing words that are honest but not inflammatory, accurate but not defeatist. He writes, the North American P-51D Mustang represents a level of fighter aircraft development that Japan has not achieved and cannot achieve with current industrial capacity. Its performance at altitudes between 15,000 and 30,000 feet exceeds all Japanese fighters by margins that cannot be overcome through pilot skill or tactical innovation. The Mustang's maximum speed of 440 miles per hour at 25,000 feet gives American pilots complete control over engagement parameters. Japanese pilots flying A6M0s, with maximum speed of 336 miles per hour at the same altitude, cannot force Mustang pilots to fight if they choose not to fight. Japanese pilots cannot escape from Mustang pilots who choose to pursue. This performance disparity creates a tactical situation that is fundamentally unwinnable for Japanese forces unless compensating advantages in numbers, positioning, or surprise can be achieved. Given current attrition rates and production capabilities, these compensating advantages are unlikely to be achieved consistently. The fifth section presents recommendations. Genda knows these recommendations will not be implemented, but he writes them anyway because his duty is to provide accurate intelligence and sound advice, not to tell his superiors what they want to hear. He recommends immediate withdrawal of A6M0 fighters from frontline service in areas where they will encounter P-51 Mustangs. Prioritization of Ki-84 Hyatt production, as this is Japan's only fighter with performance approaching Mustang capabilities at medium altitude. Acceleration of advanced fighter development programs, particularly the J-2M Raiden and N-1KJ Shiden, which have better high-speed performance than the Zero. Implementation of new tactical doctrines emphasizing altitude. Advantage and avoidance of sustained combat with superior American fighters. Expansion of pilot training programs to produce higher quality pilots capable of maximizing the limited performance advantages Japanese fighters retain. These recommendations assume resources, production capacity, and time that Japan does not have. Genda knows this. He writes them anyway. Sakai contributes a combat pilot's perspective. 8 pages of dense text describing what it feels like to fly the Mustang after years of flying the Zero, what it means for Japanese pilots facing Mustangs in combat, what tactical options remain available. He writes, the Mustang eliminates the pilot skill advantage that Japanese pilots have relied upon since the war began. A mediocre American pilot in a Mustang will defeat an excellent Japanese pilot in a Zero if the American pilot understands and uses his aircraft's advantages. The Mustang allows aggressive tactics with minimal risk, boom and zoom attacks, high side passes, dive-away disengagements. All of these tactics are enabled by superior speed and superior climb performance. Japanese pilots cannot counter these tactics with the A6M0. We can only evade, survive, and hope to inflict casualties through surprise or American mistakes. This is not a sustainable tactical situation. We are dying slowly because we are flying inferior aircraft. Better training cannot fix this. Greater courage cannot fix this. Only better aircraft can fix this, and we do not have better aircraft in sufficient numbers. Nishizawa's contribution is brief, angry, nihilistic. He writes 3 pages describing the technical performance he measured, the limits he tested, the capabilities he confirmed. Then he writes, I have fought American pilots for 3 years. I have killed 87 of them. I believed I could kill any pilot if my skill was greater. The Mustang proves this belief was false. The Mustang pilot does not need superior skill. He needs only to understand his aircraft's capabilities and refuse to fight on my terms. He can kill me whenever he chooses, and I cannot prevent this. I can only delay it by being cautious, by choosing not to engage, by running away. This is not the war one trained for. This is not the war I want to fight, but this is the war that exists. We are losing because the Americans built better tools. Spirit cannot defeat engineering. Courage cannot defeat speed. We are dying because our leaders prepared us for the wrong war. Nishizawa does not sign his section of the report. He walks out of the house and does not return for 2 days. Kuro contributes 35 pages of engineering data, performance charts, graphs, technical diagrams, propulsion analysis, structural analysis, systems analysis. His covering note is clinical. The P51D Mustang represents mature integration of advanced technologies, laminar flow wing design, two-stage supercharged engine, sophisticated fuel system, hydraulic boost controls, gyroscopic gun sight. Each technology individually is within Japan's theoretical capability to develop. The integration of all technologies into a single optimized airframe reflects industrial sophistication and engineering experience that Japan does not possess. The Packard-built Merlin engine is particularly significant, producing 1,695 horsepower, reliably at high altitude using 100-octane fuel that Japan cannot produce domestically. Japanese engines produce maximum 1,130 horsepower using 92-octane fuel. This power differential drives the performance differential. To match Mustang performance, Japan would need engines producing 50% more power than current engines. This is not achievable with current metallurgy, fuel quality, and manufacturing techniques. The performance gap will widen as American development continues, while Japanese development stagnates due to resource limitations and industrial disruption. The 4 sections are compiled, typed by a civilian typist over 2 days, bound in a folder marked Most Secret, and addressed to Admiral Suemu Toyota, Commander-in-Chief of the Combined Fleet. Through the Naval General Staff, the report is dated November 22, 1944. Genda personally delivers it to Tokyo on November 24th, hand-carrying the document to the Navy Ministry Building in Kasumigaseki. The building is a massive Western-style structure, 5 stories, concrete and brick. Damaged but functional despite multiple bombing raids by B-29s. Genda is escorted to the office of Vice Admiral Shigeru Fukudome, Vice Chief of the Naval General Staff, who receives the report and promises to forward it to Admiral Toyota immediately. Genda asks if there is anything else required. Fukudome says no, thanks Genda for his service, dismisses him. Genda leaves, expecting nothing. He is not disappointed. Admiral Toyota receives the report on November 26th, reads it over 2 days, then calls a meeting of senior staff officers for November 29th. The meeting occurs in a 3rd-floor conference room. Windows covered with heavy blackout curtains, the room lit by electric lights that dim periodically as the city's power grid struggles. 14 officers attend, representing various operational commands, technical branches, and planning offices. Toyota opens the meeting by reading selected passages from the Mustang report, his voice flat, emotionless. When he finishes, silence fills the room. No one speaks for nearly a minute. Then Captain Toshio Nato, a staff officer from the Aviation Bureau, argues that the report's conclusions are overstated, that the test pilots were influenced by flying an enemy aircraft, that Japanese pilots with proper training and tactics can compete with Mustangs. Others murmur agreement. This is comfortable territory, attributing outcomes to human factors rather than technical factors, blaming results on insufficient training or poor tactics rather than inadequate equipment. Vice Admiral Takajiro Onishi, commander of the 1st Air Fleet, responds sharply. Onishi is 53 years old, a combat veteran, an aviation specialist, and the architect of the kamikaze program. He is a realist who understands that Japan is losing the war, that desperate measures are necessary, that conventional tactics have failed. He says the test pilots included Minoru Genda and Saburo Sakai. These are not men prone to exaggeration or demoralization. If they report the Mustang is superior, it is superior. We have after-action reports from the Philippines confirming the same conclusions. Our pilots cannot engage Mustangs effectively. Our loss rates against Mustangs are catastrophic. This is not a training problem or a tactics problem. This is an aircraft problem. The Americans have built a better fighter. We must accept this and adapt our strategy accordingly. Another officer, Captain Minoru Masa from Aircraft Production Planning, argues that Japan's newest fighters, the Ki-84 Hayate and the N-1 KJ Shiden, are comparable to the Mustang and will restore balance once they are produced in sufficient numbers. Onishi asks when this will occur. Masa admits that Ki-84 production is approximately 150 aircraft per month and N-1 KJ production is approximately 50 aircraft per month. American P-51 production exceeds 500 aircraft per month. The numerical gap is widening faster than Japan can produce advanced fighters. Onishi states, "We will never achieve parity through production. The Americans are building fighters faster than we can destroy them, and their fighters are better than ours. This is a losing proposition. We need different strategies. We need to hurt them sufficiently that they negotiate rather than pursuing unconditional surrender. We cannot win an air superiority war against Mustangs. We can only inflict casualties and hope the American public loses its will to continue." The discussion continues for 3 hours, circling the same themes. The technical staff understand the problem but see no conventional solution. Japan's engine development lags America's by 3 to 5 years. Japan's industrial capacity is 1/10 of America's. Japan's aluminum supply is critically limited. Japan's fuel production is insufficient, requiring synthetic fuels that damage engines and reduce performance. Japan's pilot training program has collapsed, producing minimally qualified pilots rather than skilled aviators. Every aspect of the problem is interconnected, each issue compounding the others. The meeting ends with no concrete decisions, just a vague directive to study the issue further and develop countermeasures. Everyone in the room knows this means nothing will change. The report will be filed. The war will continue. Pilots will die flying inferior aircraft. This is what defeat looks like. Seeing the truth, understanding the problem, being unable to do anything about it. Meanwhile, at Fusa, the Mustang evaluation program continues. The aircraft is flown by additional pilots, each one confirming the original findings. In December 1944, mock combat exercises are organized, pairing the Mustang against captured Japanese fighters. The exercises are filmed for training purposes. The footage shows the Mustang easily outrunning Zeros in level flight, climbing away from pursuing Ki-43 Hayabusas, diving beyond the ability of any Japanese fighter to follow. In every scenario, the Mustang controls the engagement. One exercise deliberately gives a Zero pilot ideal conditions: altitude advantage, surprise, a favorable attack angle. The Zero pilot achieves a 6 o'clock position, a killing position, opens fire at 300 meters. The Mustang pilot pushes the throttle forward and dives. The Zero follows but cannot match the Mustang's dive speed. At 450 miles per hour, the Zero's controls are dangerously stiff, the airframe shuddering. The Zero pilot must pull out or risk structural failure. The Mustang continues diving to 530 miles per hour, pulls out effortlessly, climbs back to altitude. The Zero, slower and less efficient, takes 4 minutes to regain the altitude. The Mustang has already repositioned, regained energy, reset the fight. The Zero pilot can do nothing. One Japanese observer, a senior training officer from the Yokosuka Naval Air Group, watches this exercise and says afterward, "We are teaching our pilots tactics that do not work against aircraft like this. We are sending them to die using methods that are obsolete. I do not know what to teach them anymore." In January 1945, a second Mustang is captured, shot down over Iwo Jima with battle damage but recoverable. It is brought to Japan, repaired, added to the test program. The availability of 2 Mustangs allows more extensive testing, including destructive testing of one airframe to understand structural limits. The tests revealed that the Mustang's wing can withstand 12 G loads before failure, far exceeding the human pilot's ability to survive such forces. The fuselage structure is similarly robust, with thick aluminum skins, heavy internal frames, and extensive use of structural redundancy. The Japanese test engineers write reports describing the Mustang's construction methods: spot welding, flush riveting, alclad aluminum skins, careful attention to weight distribution and load pads. Everything reflects sophisticated engineering and high-quality manufacturing. One engineer writes, "The Mustang is over-engineered by Japanese standards. It is heavier than necessary, uses more material than necessary, costs more to produce than necessary. But this over-engineering creates robustness, durability, and survivability. The aircraft can absorb battle damage that would destroy a Japanese fighter. It can operate from rough fields. It can tolerate maintenance errors. It is designed for war, not for optimal performance. We Japanese designed for optimal performance. The Americans designed for survival. Their approach is winning." The Mustang's engine, the Packard V1650-7, receives particular attention from Japanese engineers. The engine is completely disassembled, every component measured, analyzed, photographed. The 2-stage supercharger is studied extensively, its gearing, its intercooler, its control system. Japanese engineers understand the principles but lack the manufacturing capability to replicate it. The supercharger requires precision gears, tight tolerances, exotic materials. Japan can build single-stage superchargers adequately. 2-stage superchargers are beyond current manufacturing capabilities. The engine's crankshaft is examined, revealing advanced metallurgy, heat treatment, and surface finishing. Japanese crankshafts fail after 300 hours of operation. The Merlin crankshaft is rated for over 1,000 hours. The difference is materials and manufacturing. both of which require industrial infrastructure that Japan is losing to American bombing. One engineer writes in his report, "We know what we need to build. We understand the engineering principles. We cannot manufacture it because we lack the tools, the materials, and the time. Understanding is not sufficient. Capability is what matters, and we do not have capability." By February 1945, the Mustang evaluation program is winding down. The captured aircraft have been flown extensively, tested thoroughly, documented completely. The data is compiled into technical reports that are distributed to aircraft design bureaus, combat units, training facilities. The information is valuable but depressing. Pilots receiving briefings on the Mustang's capabilities react with resignation. Experienced pilots nod grimly, having learned these lessons through combat losses. New pilots, fresh from truncated training programs, struggle to accept that they should run from enemy aircraft. But running is survival. Engaging is death. By early 1945, Japanese fighter pilots are flying defensive missions, intercepting American bombers, trying to inflict damage before being shot down. The goal is no longer victory. The goal is inflicting casualties, buying time, delaying the inevitable. The Mustang evaluation confirmed what everyone already knew: Japan cannot win the air war. The only question is how many Japanese pilots will die before the war ends. In March 1945, both captured Mustangs are destroyed in an American bombing raid on Fusa. The B-29s hit the airfield at night. Incendiaries and high-explosive bombs destroying hangars, aircraft, fuel storage. The Mustangs are burned, their aluminum airframes melting in the fires, their secrets already extracted, their usefulness exhausted. The test data, reports, and photographs are scattered. Some destroyed in the raid, others packed into boxes and moved to alternate facilities. Some documents are recovered by American occupation forces after the war. Others are lost forever. The pilots who flew the Mustangs scattered to various assignments. Genda is assigned to defend Tokyo, planning air defense operations against B-29 raids. Sakai is medically retired, his vision too damaged for further combat flying. Nishizawa is killed in October 1944, not in air combat but as a passenger on a transport aircraft shot down by American fighters. Kuro continues test flying experimental aircraft, writing reports nobody reads, watching Japan collapse. Genda survives the war, surrenders to American occupation forces, works as an advisor during the occupation, later joins the newly formed Japanese Air Self-Defense Force, eventually retires as a general. He is interviewed many times about his wartime experiences. He always mentions the Mustang evaluation as a pivotal moment in his understanding of why Japan lost the war. In a 1971 interview, he says, "Flying the Mustang was educational and humiliating. I realized immediately that we were fighting with obsolete tools against an enemy whose industrial capability far exceeded our own. The Mustang was not just a better fighter. It was a symbol of American industrial might, American engineering sophistication, American technological advancement. We could not compete with this. We should never have started a war with an enemy who could build machines like the Mustang. But we did, and we paid the price." Sakai survives, writes a best-selling autobiography titled Samurai, published in 1957, which includes extensive descriptions of the Mustang evaluation. He writes about the physical sensation of the Mustang's power, the psychological impact of its speed, the tactical implications of its performance. He writes, "The Mustang was the airplane I wish I had been flying. It was fast, strong, reliable, deadly, everything a fighter should be. The Zero was beautiful, graceful, elegant. But beautiful airplanes lose to effective airplanes when the war is real. The Americans understood this. We did not." Sakai becomes an advocate for Japanese-American reconciliation, travels to America multiple times, meets with American pilots he fought against, speaks at aviation events. He dies in 2000, age 84, one of the last surviving Japanese aces. Kuro survives, returns to civilian life, works as an engineer for Fuji Heavy Industries. Contributes to post-war Japanese aircraft development, including the T-1 trainer, Japan's first post-war jet. He gives one interview in 1985 to a Japanese aviation magazine in which he discusses the Mustang evaluation. He says, "The data was clear. The Mustang was superior in every measurable way. What surprised me was not the performance gap but the American design philosophy. They accepted weight penalties to achieve survivability. They accepted complexity to achieve performance. They accepted cost to achieve quality. Japanese design philosophy was opposite. Minimize weight, maximize simplicity, minimize cost. Our philosophy produced beautiful, fragile aircraft. Their philosophy produced brutal, effective aircraft. In war, effective defeats beautiful every time." The P-51D Mustang goes on to become one of the most successful fighter aircraft of World War II, with 15,586 aircraft produced. Mustangs achieve a kill ratio of 11-1 against German aircraft in Europe and 5-1 against Japanese aircraft in the Pacific. The aircraft serves in multiple air forces into the 1950s, sees combat in Korea, flies in civilian hands as race planes and warbird replicas. Several hundred Mustangs survive today in museums and private collections. Some still flying at air shows, their Merlin engines still producing that distinctive, powerful roar. Still capable of 440 miles per hour at 25,000 feet. Still demonstrating the engineering excellence that made them dominant in 1944 and 1945. The captured Japanese test reports on the Mustang surface in American archives in the 1950s. Historians study them with interest, finding the Japanese analysis accurate and thorough. The reports confirm that Japanese pilots and engineers understood their predicament clearly. They knew their aircraft were inferior, they knew their recommendations would be ignored. They documented the truth anyway, creating a historical record, bearing witness to what they found. The reports are significant because they provide the enemy's perspective. The view from the losing side, the moment when defeat becomes mathematically undeniable. The Japanese test pilots who flew the Mustang understood, perhaps better than anyone, that the war was already lost. They were documenting the gap between Japan's capabilities and America's, measuring the distance from where Japan stood to where Japan needed to be, and discovering that the distance was too great to cross. The broader lesson is about industrial capacity and technological development during total war. Japan began the war with advantages, experienced pilots, tactical doctrines proven in China, advanced aircraft like the Zero that dominated early engagements. But Japan's industrial base was limited, its access to strategic materials was constrained, and its technological development was incremental rather than revolutionary. America began with disadvantages: inexperienced pilots, inadequate tactical doctrines, mediocre aircraft. But America's industrial capacity was vast. Its access to resources was unlimited, and its technological development was rapid and adaptive. The Americans learned from their mistakes, designed new aircraft to counter enemy advantages, produced those aircraft in overwhelming numbers. The Mustang was not a brilliant innovation. It was a practical solution, combined the best American airframe with the best British engine, optimized for performance at critical altitudes. Build thousands of them, train pilots to exploit their advantages. This approach, pragmatic and industrial, defeated Japan's approach, which was aesthetic and individual. The Mustang evaluation also reveals cultural differences in how defeat was processed. German test pilots who flew captured Allied fighters wrote honest reports acknowledging Allied superiority and making rational recommendations. Those reports were largely ignored by ideologically driven leadership, but the reports existed and were acted upon by technical staff who understood reality. Japanese test pilots wrote similarly honest reports, but the institutional response was different. Japanese culture, with its emphasis on honor, duty, and collective identity, struggled to process information that implied inferiority. Admitting that American aircraft were better meant admitting that American civilization was more advanced, which contradicted fundamental assumptions about Japanese superiority. So the data was acknowledged but not acted upon, filed but not integrated into strategy, recognized but not accepted. The result was continued use of obsolete tactics and equipment until the final collapse. The human cost of this denial is difficult to quantify but impossible to ignore. How many Japanese pilots died flying Zeros against Mustangs when their superiors knew the Zero was inferior? How many attacks were ordered against targets defended by Mustangs when planners knew the attacks would fail? How many young men were sent into air combat with inadequate training, flying inadequate aircraft, against an enemy whose technological superiority had been documented and filed away? The numbers are unknowable, but the phenomenon was widespread. By 1945, Japanese fighter pilots had life expectancies measured in weeks. They flew, knowing they would probably die, hoping to inflict some damage before being shot down, their courage unquestionable, their cause hopeless, their sacrifice demanded by a system that could not admit defeat. The technical comparison between the Mustang and the Zero is a case study in design evolution. The Zero was designed in 1937, 1938 for a specific set of requirements. Long range for carrier operations and land-based missions over China, excellent maneuverability for air superiority, low weight for high performance from limited engine power. The design succeeded brilliantly, creating an aircraft that dominated early war combat, but the Zero's design made trade-offs that became fatal vulnerabilities as the war progressed. No armor meant pilot casualties were high, no self-sealing fuel tanks meant fires were common, lightweight structure meant fragility under combat stress. The Zero was optimized for a short, victorious war. The Mustang was designed in 1940 to 1943 with different priorities. High speed for bomber escort and interception, high altitude performance for combat over Europe, survivability for bringing pilots home, long range for penetration missions. The Mustang was optimized for a long attritional war, By 1944, the type of war the Mustang was designed for had become the reality, and the type of war the Zero was designed for had disappeared. Doctrine and design had diverged, leaving Japanese pilots flying aircraft designed for yesterday's war. The engine technology gap is particularly revealing. The Zero's Nakajima Saka 21 engine produced 1,130 horsepower from 27.9 liters using a single-stage supercharger. Simple, reliable, adequate for operations below 20,000 feet. The Mustang's Packard V1650-7 Merlin produced 1,695 horsepower from 27.0 liters using a two-stage intercooled supercharger. Complex, sophisticated, optimized for high-altitude operations. The 50% power advantage drove the performance advantage, but the power advantage reflected deeper industrial capabilities. The Merlin required precision manufacturing, advanced metallurgy, high-octane fuel 100-octane versus 92-octane for Japanese engines. America could provide all of these. Japan could not. The engine gap was not just about engineering. It was about the entire industrial system supporting the engine. From oil refineries producing high-octane fuel to steel mills producing specialty alloys to factories with precision machine tools. Japan lacked this supporting infrastructure, and building it would have required years and resources Japan did not have. The armament comparison is equally stark. The Mustang carried 6.50 caliber Browning M2 machine guns with 1,880 rounds total. Later versions carried 4 guns with 1,600 rounds. The firepower was devastating, with all guns synchronized to converge at 300 yards, creating a cone of fire that could destroy an aircraft in a 1-second burst. The Zero carried 2 7.7mm Type 97 machine guns and 2 20mm Type 99 cannons, with limited ammunition 60 rounds per cannon. The Japanese cannons were more destructive per hit, but had lower hit probability due to slower muzzle velocity and greater drop. The American 50 caliber had flatter trajectory, higher muzzle velocity, more ammunition, allowing longer bursts and greater hit probability. In practice, American pilots could fire longer, hit more often, and destroy targets more reliably. The K-14 gyroscopic gun sight in the Mustang computed LED automatically, while Japanese pilots used iron sights requiring manual estimation. Technology multiplying firepower created overwhelming advantage. The range comparison reveals interesting complexities. The Zero had longer absolute range, approximately 1,200 miles with drop tank versus 950 miles for the Mustang with drop tanks. But range is more than fuel capacity. It is fuel efficiency under combat conditions. The Zero achieved its range through minimalism, lightweight structure, efficient cruise, minimal equipment. But any combat maneuvering reduced range dramatically. The Mustang achieved its range through capacity, large internal fuel tanks, efficient aerodynamics, powerful engine that could be throttled back for economical cruise. Combat maneuvering reduced range, but not catastrophically. More importantly, the Mustang's self-sealing tanks meant battle damage rarely caused fuel loss, while Zero fuel tanks, non-self-sealing, often leaked or burned when hit. Effective combat radius accounting for fighting and damage favored the Mustang despite its lower absolute range. Japanese test pilots noted this but struggled to quantify it. How do you measure the value of surviving to use your fuel? The post-war legacy of the Mustang evaluation is mixed. The technical data contributed to American understanding of Japanese perceptions and confirmed that American aircraft development had succeeded in its goals. The personal stories of the Japanese pilots who flew the Mustang became part of aviation history, recorded in interviews, memoirs, and historical accounts. But the strategic impact was zero. The evaluation occurred too late in the war to change outcomes. By November 1944, Japan's situation was desperate. The Philippines were being invaded. The B-29 campaign against the home islands was intensifying. Fuel shortages were crippling. Pilot quality was plummeting. Knowledge that the Mustang was superior made no difference because Japan lacked the time, resources, and industrial capacity to respond. The evaluation documented defeat but could not prevent it. The psychological dimension is perhaps most significant. The Japanese pilots who flew the Mustang experienced a moment of clarity, a recognition that their beliefs about Japanese superiority were false, that the ideology sustaining the war effort was built on illusions. For men like Genda, educated, intelligent, professionally competent, this recognition was liberating in a way. It freed them from false hope, allowed them to see reality clearly. For men like Sakai, who had built their identity around being superior warriors, the recognition was devastating. It meant everything they had sacrificed for was based on a lie. For men like Nishizawa, already psychologically fragile, the recognition pushed them toward fatalism and self-destruction. The Mustang evaluation was not just a technical exercise. It was a confrontation with truth that shattered myths and forced individuals to choose how they would respond to undeniable defeat. The final chapter of the story occurs after Japan's surrender. American technical intelligence teams arrive in Japan, seize documents, interview personnel, recover test data. They discover the Mustang evaluation reports, along with evaluations of other Allied aircraft. The reports are translated, analyzed, distributed to American aircraft manufacturers and military research facilities. Engineers at North American Aviation, manufacturer of the Mustang, read the Japanese reports with satisfaction. The Japanese confirmed that the Mustang was as good as American pilots said it was, that the design decisions were correct, that the aircraft fulfilled its mission. But the reports also revealed Japanese desperation, Japanese recognition of defeat, Japanese understanding that they were fighting with inadequate tools. American analysts recognized that Japan's collapse was not just military, it was psychological. When your best pilots fly the enemy's best aircraft and conclude that they cannot win, morale collapses, fighting spirit evaporates. Defeat becomes inevitable not through being overwhelmed, but through loss of belief. The survivors carried these experiences through their lives. Genda, in his post-war career, always emphasized the importance of matching doctrine to capability, of honest assessment over wishful thinking, of building what works rather than what looks impressive. He became an advocate for realistic defense planning, often citing the Mustang evaluation as an example of what happens when nations fool themselves about their capabilities. Sakai, in his writing and speaking, emphasized the human cost of technological inferiority the young pilots sent to die flying obsolete aircraft, the institutional failures that prolonged a war Japan had already lost. He argued that understanding when you cannot win and accepting the need to stop fighting is not cowardice, it is wisdom. The Japanese leadership's failure to accept reality in 1944, when the war was clearly lost, cost hundreds of thousands of additional lives in a futile attempt to achieve impossible goals. The story of Japanese pilots flying a captured Mustang is ultimately about the intersection of technology, ideology, and human experience. The pilots who flew the Mustang were skilled professionals doing their jobs, measuring performance, documenting reality, reporting truth. The system they served was incapable of acting on that truth because the truth contradicted fundamental beliefs about Japanese superiority and destiny. The result was a tragedy that played out across thousands of individual stories, pilots flying inferior aircraft, dying in unwinnable battles, sacrificing themselves for a cause that was already lost. The Mustang evaluation is one window into this tragedy, a moment when the gap between propaganda and reality became too wide to ignore. When measurement replaced mythology, when data defeated denial, the men who flew the Mustang understood what it meant. They wrote their reports, filed their data, and watched as nothing changed. They had done their duty. They had told the truth. That the truth was not heard, was not acted upon, was not allowed to change strategy. That was not their failure. That was the system's failure. And the price was paid in blood. The Mustang evaluation is one piece in the larger mosaic of World War II's technological race, where engineering decisions made years before determined who lived and who died when the combat came. If you want more deep-dive historical investigations like this, built on primary sources and focused on the human stories behind the machines, subscribe now. We publish these stories every week, uncovering what others miss. Thanks for watching.